This is a medium difficulty problem. However, if you are not aware of the concepts, it can be a difficult problem. In this problem, there is a solid sphere, a solid disk, and a hoop ready to roll on the inclined plane. Let me clarify on the hoop. It is like a hollow cylinder with mass around the circumference. You are asked to find which one of them rolls the fastest and what are their velocities when they have rolled a distance of 10 meters. We will solve the problem in two different ways, which will clarify a lot of your concepts along the way. Pause the video and read the problem carefully and think before we proceed with the answer. Let's proceed. In the first method, we use conservation of energy to solve the problem. Before we proceed, let us get all the conditions of the problem. We have drawn the figure with one of the object. H is the height it falls after rolling 10 meters. So this is 10 times sine of 30 degrees. Moment of inertia of sphere, disk, and hoop are known. Now let us proceed with the answer. Based on conservation of energy, if it drops a height h, the potential energy mgh should get converted into kinetic energy. But wait, here we have two kinds of kinetic energy, translation kinetic energy and rotational kinetic energy. The translation and kinetic energy, which we all know, is half mv square, and the rotational kinetic energy is half times moment of inertia, which is I, times angular velocity squared. Hope you have studied the way to easily memorize the analogy of half mv square in rotation. The mass becomes moment of inertia, I, and the velocity becomes angular velocity. Now, translation velocity is related to angular velocity as v is equal to r times omega. It's not very obvious, and we'll prove it in the next slide. For now, let's proceed with this assumption. We substitute v for r omega, and rest becomes straightforward, simple algebra. We get this, and from this we can easily get angular velocity or translation velocity. We have got our answer to calculate the translational velocity. But let me focus on this colored equation. It's a beautiful equation. As you can recognize, each terms from translational kinetic energy, rotational kinetic energy, or potential energy. Yet, it solves the essence of the problem that I like you to see. You see, all the green colored are constants for the problem. Mass, radius, height are constant. Only moment of inertia and angular velocity are different for different objects. So if you have less moment of inertia, you need to have more angular velocity to have the right hand side the same, which is mgh. So it follows that the sphere having minimum moment of inertia will have maximum angular velocity, which will mean maximum linear velocity. The hoop having the minimum moment of inertia will mean it rolls the slowest, which also means linear velocity is slowest. So qualitatively, we have solved the answer with this equation. Of course, for calculating the exact velocity, we need the final formula. We will do that in a moment, but for now, you may like to pause the video and think these steps again. It is possible that you may find more insight than I could. Let us proceed. Now let us evaluate the velocities and get the answer to the problem. This is the formula for the answer. We know h, we know moment of inertia of all the three objects, sphere, disk, and hoop. Note that mass and radius will cancel and we get pure number. We can use calculator to do it and we get these velocities. As expected, the velocity of sphere is the greatest and velocity of hoop is slowest. I would also like you to get the same answer by using WolframAlpha. It is a free online software. It can be a bit fussy, but it is the best software for doing symbolic calculations. Go to wolframalpha.com, type in the command as shown in the purple box. The command is also mentioned in the description of this video, so you can cut and paste. It is important to note that space between variables or asterisk means multiplication. Strangely, the variable I, which was meant for moment of inertia, is not accepted. So I used psi, which is a Greek letter. And lastly, slash and dot is for substitution. The beautiful part of this command is it is able to solve for all the three velocities simultaneously. But amusingly, as you can see, it is not able to cancel the radius. So we will do it ourselves. Hope you are able to get the answer and feel proud that you are able to do it yourself. Pause the video if needed before we proceed. Let us proceed. In this slide, we will keep our earlier promise to show the relation between translational velocity and angular velocity. See the figure and imagine you have a cylinder of radius r which is painted green on the outside and the paint is wet. If you happen to roll the drum, it would have moved a distance of 2 pi r in one revolution. I hope you agree with me. If you agree with me, then you will also agree that the drum rolls by a small angle delta theta. The corresponding arc will be equal to distance traveled delta d. Mathematically, that is given by this relationship. Once you see that these two are equal, it becomes very easy from here. Divide by delta t and we get a relation between translational velocity and angular velocity. Let us write nicely to remember the relation. Now we will not stop here. Let us take another derivative and now we get a relation between angular acceleration and linear acceleration. You can pause this video to think it over before we proceed. Let us proceed. As promised, we will solve with second method by involving torque. Let me squeeze all in this one slide. It is going to be intense and feel free to pause at various points. Let us begin. Along the x-axis as shown, there are two forces acting on the object. Note that the x-axis is along the inclined plane. One is the force mg sine phi, which is reduced gravitational force due to inclination. Second is the frictional force due to which the object is not slipping. The net force is not zero, so it will accelerate as given by Newton's second law. The friction force rotates the object, hence there is a torque given by this equation. The torque is radius times the frictional force, which is also equal to moment of inertia times angular acceleration. The angle between radius vector and frictional force is 90 degree. Hence the cross product sine angle is 1. In friction force equation, we can substitute the angular acceleration with linear acceleration. In previous slide, we derived this relation. So now the first equation reduces to this equation with a bit of algebra. Multiply 2 times d both the sides, where d is the distance rolled along the inclined plane. By multiplying 2d, we get this equation. D sine phi is the height h that object has moved vertically. Now let us look at our old three great equations of motion. We pick the third equation to substitute for 2d and we get this equation. Since the objects start at rest, the initial velocity is 0. So we now solve for the final velocity, and this is what we get. Exactly the same we got from the first method. I hope you enjoyed the derivation here. In this last slide, let us summarize. We solved the problem by two methods. One by conservation of energy method, which was quite easy. Second method was using the force and torque equation. We also used WolframAlpha, which you can consider as analytical calculator, to solve all the three in one command. We find the sphere rolled is the fastest because moment of inertia was the least. We hope you have enjoyed the video. Bye bye.